Okay, so let's talk about the origin of magma. What is magma? Magma, quite simply, is molten rock. When it's below the surface, we call it magma. When it reaches the surface, we call it lava, but it's basically molten rock. It's what makes up the mantle, and this, by studying lava, we can see what's in the mantle. Now, to melt rock, it requires a couple things: heat, pressure, and water content. To melt rock, we require a lot of heat, and we can get heat from depth. The deeper you go into the earth, the warmer it gets, but it doesn't get hot enough to melt rock. So we have to add additional sources of heat, and the additional sources of heat comes from this friction of the plates. So as the plates are rubbing against each other, it generates some heat, and that'll help melt rocks, and also the mantle itself. The mantle itself is going to be a lot hotter since it is molten rock, and it'll melt rocks that come into there. And we saw that during convergent subduction areas. Also, the heat will rise. So if we have magma plumes or magma bursts coming up, then what happens is this magma will melt the rock around it. Okay, we also have pressure, and pressure is going to be a little more interesting. The deeper inside of the earth, we get more pressure, and that pressure can kind of squeeze rock together and keep it from melting. It'll keep the pieces close together. When we release that pressure, we get what we call decompression melting. So what that means is if I have a piece of rock here and I'm applying a whole bunch of pressure to it, it'll keep all those particles together in a solid form. But once I remove the pressure, we get rid of the pressure on it, it allows the little bits and pieces to all move apart from each other, and we get what we call decompression melting that way. And then finally, we have water content. And rocks that have a little more moisture in them tend to melt at a cooler temperature than rocks that don't. So a couple percent of water is going to translate to hundreds of degrees cooler. And that helps out too. If we can get a little bit of water into the rocks, into the minerals, then what's going to happen is they'll melt a little bit faster. Now, we see a lot of volcanoes happening at the boundary areas. We talked about two of them, and the two we wanted to talk about are divergent and convergent boundaries. At divergent boundaries, if you can remember, we have two plates that are moving apart. So as the crust moves apart, it's going to expose the mantle, and the mantle will rush up through this opening, and then we'll get these volcanoes there. So at divergent plates, remember we have these plates that are moving apart, they create this rift, and in this rift is where we have magma come up and we have volcanism happening there. Convergent plates are going to be a little bit different. At convergent plates is where we have two plates, and these two plates are going into each other. Now, generally, one plate will be a little more dense than the other, and that dense plate is going to subduct under it, and we can see that subduction going on here. As it goes down, this plate's going to get a little bit warmer, it's going to get a little hotter, and it's going to start melting, and we can kind of see that going on here. And as it melts, that less dense rock is going to work its way upwards. We can see it working its way upward here, and then we get these volcanoes here. If it's in continental crust, we have these continental volcanic arcs. And remember, if it was oceanic, we had an oceanic volcanic arc. So we can see at these boundaries, we have this volcanism going on, whether we're splitting it apart at a divergent or whether we're melting down more material and allowing that to rise up. Now, you may have heard this term before. It's called the Ring of Fire. And the Ring of Fire is this area that you can see in the map that's in this kind of peachy reddish kind of color. What it's showing us is where we see a lot more of our volcanic activity, a lot more of our earthquake activity, and it's also the boundary of the Pacific Plate. So we see where all these boundaries are going on, and that gives us this idea of where we have these earthquakes and where we have these volcanoes happening all the time. Now, not all volcanism happens at the boundaries. We can have intraplate volcanism, and what that means is if we have our large plates or tectonic plate here, we can have volcanoes happening in the middle of them, and that's what this intraplate is. Now, where this occurs is where we generally will have what we call a hot spot, and that hot spot is where we see this mantle plume. So we'll see this magma rising up here in one area, and it'll actually break through the oceanic lithosphere and form a volcano on the ocean floor. And over time, that volcano can grow and grow and grow and become an island like it has in Hawaii. Now we know that the plate is moving, and that plate is moved over this hot spot, so the older islands are the ones that are going to be further away, like Hawaii is about 3.8 to 5.6 million years old. But we also have the island of Hawaii, where we have currently Mauna Loa and Kilauea, two active volcanoes over the hotspot that are still showing activity. So intraplate happens over what we call hotspots. Okay, so that's it for our short introduction to volcanoes. Good luck on the lesson and the quizzes, and we'll see you in the next video. So if we look at the factors that affect an eruption, most of them are going to come down to this magma composition. What's the magma made of? And we can see, if we recall back to our discussion on igneous rocks, that we had basaltic, granitic, and then these andesitic, and those are all based on the silica content. For eruptions, however, we're going to tend to look at something a little different. We're going to look at its viscosity and then its gas content. Now, viscosity is resistance to flow. So something that's highly viscous would be like maple syrup, and something that is a low viscous would be like water that flows easily. So our basaltic is going to be least viscous, which means it's going to flow. And then our granitic is going to be greatest viscosity, and that means it's going to kind of like just ooze. We'll call it a little different way to phrase it. So now, if I have something that's going to flow, then it's going to be a nice smooth eruption. As opposed to where it's oozing, it's going to kind of bubble over and boil over and things like that. It doesn't want to flow as easily, so you kind of have to force it out. Now, we also want to talk about gas content. Because I am very low viscous, the gases can escape easily, and there's a little gas content here, and that all results in a nice smooth eruption. Okay, and that's how we build our shield volcanoes and our basalt plateaus. Now, if we have a lot of gas, then that gas gets trapped up in this oozy kind of lava. Then we build up pressure, and then when that gas finally gets too big, it forces out this stuff. And that's how we get our really big explosive volcanoes. Okay? And that's where we see pyroclastic flows and things of that nature. Now, cinder cones can be a little bit both ways. We can kind of see them there. We also see them down here. But as long as we have a low viscosity and low gas rate, we have a smoother eruption. When we increase that viscosity, that resistance for the magma to flow, and we up the gas content, that's when we get our explosive volcanoes. Now, what kinds of things come out of volcanoes? Well, we have three basic types here. The first one we're going to talk about is our lava flows. And mostly what we're talking about is when we have a nice flowing eruption, we can have two different kinds of lava. We can have what we call pohoihoi here, and pohoihoi is just going to be a smooth flowing. When it dries, it's going to be like kind of rippled and smooth and things of that nature. The on the other hand, is where it's a little bit slower, there's a little bit more gas in it, and that ends up making these really sharp lava rock areas and things of that nature. So we can see that the flow is going to be determinant on its viscosity. If it has a low viscosity and it flows smoothly, we have the pohoihoi here. And if it's going to be a little bit more viscous, we're going to talk about this flow here. So where it gets to be kind of rough and pokey and nothing you'd want to walk on. Now, volcanoes also release a bunch of gases when this happens. And that's kind of what we think formed most of the early atmospheres, these volcanic gases. And we notice things like carbon dioxide are going to come out of them, and water vapor, steam, things of that nature are going to be coming out of these volcanoes. We also have what we call pyroclastic materials, and these are going to be solids that are ejected out. Now, we have three different classes, and it's based on size. If it's less than 2 millimeters in size, we call it ash. If it's between 2 and 64 millimeters, we call this lapilli, or sometimes we'll call it cinders. And when it gets to be larger than 64 millimeters, that's when it's on the ground. It's a block if it pops out. And if it goes airborne, then we tend to call those bombs. So as you can see, there's a lot of different things that'll come out of a volcano. It's not just simply a nice flow of lava. We also have the gases and other pyroclastic materials as well. So let's look at the typical structure of a volcano. We start off with the magma chamber, and this is where the molten material is. That magma chamber will lead up through a pipe, sometimes it's called a conduit, to the vent. And the vent is going to be the actual opening where it comes out of. Now around this vent we have what we call the crater. Okay, and that's going to be this rocky material that you see surrounding the vent here. And then from there is where we start to see where we have this buildup. And you'll notice that we can have, in this one here, we have pyroclastic materials that have layered and lava flow layers. So this is going to be a composite volcano. But the main parts I want you to know is this magma chamber here that leads up through the pipe or the conduit and out the vent. Now we do have three major types of volcanoes that we want to talk about, and I'll go over them a little bit more in the lesson. We have our shield volcanoes, which are going to be our largest, and that's where we're going to have a flow-based system. So what we have is we have the vent here where it comes out, and we're going to have a lava flow, and then we'll have another lava flow, and then we'll have another lava flow, and another lava flow. And these get to be really big. They have a nice gentle slope, and you can kind of see that it looks like an old-fashioned shield just kind of lying on its side. Now the smallest of our volcanoes are these cinder cones, and the cinder cones is where we have these pyroclastics that are thrown out, and then they just kind of like start to pile up. Our cinder cones are smaller. They tend to have steeper sides to them because anything that's too wide is just going to run right down and form like a base layer. So we have these tiny little cinder cones. And that leads us to the third type, which is the composites. And the composites are going to have elements of a shield volcano as well as elements of a cinder cone volcano. It's going to have a shield volcano things because you'll notice that there's going to be layers of lava flows. We'll see those. But also intermixed with that, we're going to have these pileups of cinder cones. And if we start to draw it out a little bit more like this, you can kind of see this alternating band is going to result in our shape of a composite cone. So if we look at our volcanoes, our shield volcanoes are going to be very long and broad and big. We're going to have a composite, which is going to have kind of both setups there like this, is how they kind of tend to be. And then we have our tiny little cinder cones here, which are going to be really steep. So we can see the three different kinds of volcanoes. Now here we can see our three types of volcanoes again. We have our large shield volcano, and the example here is the Mauna Loa in Hawaii. It's one of the largest volcanoes on the planet, and it's by size. It's just huge. It's an island almost. We next go to our composite ones, and we can see Mount Rainier here, and they can be large as well, but these are all drawn to scale, so you can kind of see how much bigger a shield volcano is than a composite. And then down here we have our cinder cone, and we're going to use Sunset Crater in Arizona, and you can see the size variation between the three different types of volcanoes. Now we can have other kinds of volcanic landforms. You can have a caldera. So if we have our volcano here, and then at the very top it kind of sinks in. So if this magma chamber collapses and it kind of sinks down, we can have what we call a caldera. And some of those calderas can fill up with water, and like we have Crater Lake would be a good example. So we'll have a lake on top of an old extinct volcano. Sometimes those volcanoes can erupt again, and you can form little islands from a cinder cone that would form. But we have these different, this depression is called a caldera. The next one is a neck. And a neck is where we have this hardened volcanic pipe. So if you remember that volcano, and we'll draw another real simple volcano here, we have that volcano and it had this neck, the conduit here. Well, if that all magma solidifies, then it tends to be a little bit stronger than the surrounding material, especially if it's a cinder cone where it's going to be like just this pyroclastics. All of this will erode away and you end up with just this one solitary pipe. So you're just going to end up with just that pipe coming up here, this neck, so to speak. And examples would be like Devil's Tower or Shiprock, where you'll have just that neck that's been exposed from erosion. And then finally we have these lava plateaus. And these lava plateaus will come where you have a fissure, and it's just this flow that's coming out. And it's just these broad areas of large volcanic activity. And you can see that up in the Cascades. Up in Canada, there's a few, and even if you go to like Idaho, you'll see these large areas where you just have this massive lava plateau hanging out. Okay, so let's talk about volcanic hazards. And there's a bunch of different ones that are going to happen. Probably the most obvious is going to be the lava flow, and you can see that one coming here down the side of the mountain here. And that's just where lava is going to be flowing from the vent downwards. And if you had something in the way, like a house or a village, that lava would basically just kind of melt it away, burn it away as it comes through. Some of the other ones we also notice are these ash. And you can see that in this one we have this big ash cloud here. And the ash has a couple different things to it. It can fall down and cover everything and choke out plants and get into like animals' lungs and things of that nature just from the falling ash. But also it can mix in with the moisture in the air and we can get acid rain coming down as well. So the ash clouds can create issues with travel just because of limited visibility. They can block out sun. One of the cool things about them is when you have a big eruption and it throws that ash up, you generally tend to have better sunsets for a while afterwards. You also can have these pyroclastic flows. And the pyroclastic flow here is a mixture of gases, pyroclastic materials. They move very quickly. When you hear about the city of Pompeii next to Mount Vesuvius, that was a pyroclastic flow that came through and it instantaneously killed everybody and preserved them at once. So these are very toxic, quick moving clouds that'll just kind of like choke, poison, cover with a fine layer, and then it can preserve an entire city like it did with Pompeii. And then the last one we'll talk about is this lahar, these mud or debris flows. And that generally happens when you have snow cap on top. So here you can see there's a little bit of snow here. And as that volcano erupts, that snow is going to melt. It's going to mix in with the mud, and you get these massive mud flows that'll be coming down as well. Okay, so that's it for our video. As always, the lesson will go into more detail. Good luck on your quiz, and we'll see you in the next video. Okay, so when we're talking about intrusive igneous activities, what we're talking about, not the extrusive stuff, which we can kind of see here as being these explosions in these volcanoes, but intrusive we call plutons. And we're going to see a bunch of different varieties of those and what they do. And that's what we'll talk about in the next slide. So when we're talking about plutons, we have to talk about several different things. One of them are going to be these sills down here. And sills are where we're going to have this magma come up and it's going to fall in between layers or within the layers of a rock. And it's going to be almost always horizontal with the surface. And it's just this where this magma will go seep into these little between the layers of the rocks and it'll harden that way. Now, we can have a larger formation, which is this laccolith, and that's going to be kind of a dome, lens-shaped dome of magma that's going to cool under the surface. But as it fills, it's going to cause the surface to kind of upwarp a little bit. So it's a big lens-shaped, larger structure. We can also have what we call a dike, and a dike is different from a sill and a laccolith in the sense that a dike will go across rock layers. So it'll find a crack or it'll find a fault, and if it finds this little crack between the layers, it'll actually fill that one in, and that's how we'll form these dikes there. So in summary, a sill is going to form a horizontal band within a layer. Laccoliths are going to push overlying layers upwards, and then a dike is going to cut across the rock layers. Now here we can see our plutons again. We have our sill here, and notice that it's in between the layers. We have a dike that's going to cut across the layers, and then we have a laccolith which is going to kind of bubble up and deform the layers above it. We also have a new term, and that's this batholith here. And batholiths are going to be large. If you notice sills, dikes, laccoliths, they're not too big in structure, but batholiths are going to be like hundreds of kilometers big. Okay, so square kilometers. Now, if the laccolith is forced up to the surface, then we can get erosion and we can get mountains that are going to form from that one. And we'll talk about that a little bit more in the lesson. So our smaller ones are plutons, and those we can see here. And if these plutons lump together, join together, they can form what we call a batholith, and sometimes those will form their way up to the surface. So that's it for our video. As always, good luck on the lesson and good luck on your quiz, and we will see you in the next video.